Hello everyone, today we are going to discuss 2 to 3 questions from the IIT JEE Advanced section, and here is our first question. The question says atom X occupies the FCC lattice sites as well as alternate tetrahedral voids of the same lattice. The packing efficiency in percentage of the resultant solid is close to. Let us see the solution. Now, the atom occupies the FCC lattice as well as alternate tetrahedral voids. So, first of all, if I want to calculate the packing efficiency, I need the number of atoms, right? Multiply by the volume of each atom, just 4 by 3 pi r cube, divided by the total volume available, that is A cube into 100. This is the formula for the packing efficiency. Now, in order to find the packing efficiency, I require two things, that is Z, number of atoms, where I also incorporate the contribution of each atom, and I need the A and R relation. So for Z, this is basically, Z is calculated as, since this atom occupies the FCC lattice, you know the Z value is 4, right? So the Z value is 4. Why? Because 8 atoms are at the corners of the cube and 6 atoms are at the face centers, which are having 1 by 2 as the contribution at the face center and 1 by 8 as the contribution at the corner. So this is basically 8 into 1 by 8 plus 6 into 1 by 2. So this is how I got 4, and it is also occupying as well as the alternate tetrahedral voids. We know that there are 8 tetrahedral voids, right? So alternate means that I will include 4 tetrahedral voids. So Z comes out to be 8. Now, how will we calculate A and R relation? For that, let us see, suppose if this is a cube, let me draw it. This is your cube. Or let me use the tools for this shapes. This is the cube, right? Now suppose for the location of the or the type of void, let us consider 4 atoms. This corner atom, the atom of this face center, the atom here at this face center, and the atom here. So if you join this, you know this forms a tetrahedral shape like this, right? Similarly, I can choose the atoms here, this atom, the atom of this face center, the atom of this face center, and this corner atom. So here also I get something like this. Yes? Now, if I ask you what is the position of a void, of a tetrahedral void in a FCC lattice, then if you join this, this is my body diagonal, right? This is my body diagonal, and I have the tetrahedral void somewhere here. This is my tetrahedral void. Right? These are my tetrahedral void. Now, at each body diagonal of a cube, I am having 2 tetrahedral voids. Now, since there are 8 body diagonals, so there are 4 body diagonals, so I have 8 tetrahedral voids. Now, and this is the center of the body diagonal. So how to find out Let me take this body diagonal here. So this is something like this. This is one atom at this corner. This is other atom at this corner. This is the tetrahedral void. This is the center of the body diagonal, and this is another tetrahedral void. So if you see, you know this body diagonal is root 3a. If I consider a to be the edge of the cube, right? If a is the edge of the cube, then this body diagonal is root 3a, and you know that this is r plus r plus r plus r. So can I say that basically root 3a, or I can also call it that if I want to find out the relation between a and r, then if I consider this distance is 2r, right? This distance is 2r. So, and this is root 3 by 4. This is root 3 by 4 because this is root 3. Total is root 3a. This is root 3a by 4 because I have divided it into 4 parts. So, root 3a by 4 is equal to 2r. Is equal to 2r. Now, if you want to find out r is equal to root 3a by 8a. This is a relation between a and r. If you put these values in this formula, then z comes out to be 8, 4 by 3 pi r. In place of r, I am writing root 3a by 8 whole cube into 100 divided by a cube. And when you solve this, you will get approximately 35%. You will get approximately 35%. So B is the correct answer. Now this is something like, this is exactly like diamond. This is diamond-like structure. This is basically diamond-like structure. Diamond-like structure, right? There the value of z is 8 and the relation between a and r is that root 3a by 4 is equal to 2r. So this is how I will calculate the packing efficiency in this question. Now let us move to the next question. The next question says, treatment of D-glucose with aqueous NaOH results in a mixture of monosaccharides which are. So this is basically a question from epimerization. This is a question from epimerization. Now, epimerization or enediol rearrangement. Enediol rearrangement. Because I will end up getting the epimers, like C2 epimers in this question. So epimerization, and I will also get ketose via enediol rearrangement. Let us see this question. So this is my glucose. Right, let me write it CHOH whole thrice and CH2OH. This is my glucose. Now in the presence of a base, what will happen? Base will abstract this particular H, right? And I end up getting the carbanion like this. This is CHOH whole thrice and CH2OH. Now you know that this is resonance stabilized. Yes, this is resonance stabilized. So this is basically resonance stabilized enolate ion. This is resonance stabilized enolate ion. Resonance stabilized enolate ion. Now, the hydrolysis of these ions, like if I add H to this carbon or I add to this oxygen. So basically, protonation at this carbon results in the regeneration of the stereo center that is lost in the first step, right? And a protonation at this H will result in the enediol rearrangement. Let us see. So let me perform the protonation on this carbon. So hydrolysis of this results in the regeneration of, and now since this protonation can happen from both the sides, so it results in the formation of epimers, which we call C2 epimers. So this H can be, protonation can take place from either side, right? This, right? So here the stereo center is regenerated. Stereo center is regenerated, right? Plus I will also get something like this, CHOH whole thrice, and this is CH2OH. So this is your D glucose and this is your D mannose. D mannose is C2 epimer of D glucose. It is your C2 epimer of glucose. C2 epimer of glucose. Now, if we perform the protonation over here, let us see how will we get ketose, right? So, now, I'll take this. Negative H. This is OH. Here I'll get CHOH whole thrice, and this is C2OH. So if I perform the protonation on this oxygen, then I end up getting something like this, right? So this is what I'll get. H, CH whole thrice, and this is CH2. So this is what I get after performing the protonation on this oxygen. Now in the next step, if I have the base, what will happen? So you know that this is your enol form. Now what will happen? Basically, I'll get something like this. O negative. If I abstract this particular H, then CHOH whole thrice, and this is your CH2OH. So this is what I get. So in the first step, I have performed the protonation on this oxygen. What I end up getting is that ion. So now what will happen? You know that this is resonance stabilized like this. This is your enolate ion. Again, this is your enolate ion. What will happen? So I have C double bond O, and this is CH negative, and OH is there. Let me write it this way. This is C double bond O. Basically this goes here, and this is your C negative, OH and H, right? And this is CHOH whole thrice, CH2OH. Now what will happen in the next step? Now in the next step, if I perform the protonation, what do I get? CH2OH, C double bond O, right? This is CHOH whole thrice, and this is CH2OH. So what is this? This is a ketose, and this is your fructose. Right? A ketose. So basically in this question, D-glucose has been converted to, basically from D-glucose we have got D-mannose, and fructose via epimerization and enediol rearrangement. I hope these questions are clear to you. We'll meet in the next class. Thank you so much.